Okay, let's check this bad boy. I can check all my work by differentiating and just being really specific. That's tangent of 1/2 x to the 6 plus c. So the 2 hangs out. Chain rule. Start on that outside, multiply by that exponent. Decrease that exponent by 1. Chain rule times the derivative of the interior. Derivative of tangent is secant squared. So I took care of the tangent, but this is actually a repeated chain rule. Derivative of tangent gave me the secant squared. Now another chain rule times the derivative of the inside, derivative of that 1/2 x, 1/2, and then derivative of that c on the end would be 0. The 2 and the 1/2 cancel, and I've got 6 tangent to the 5th, 1/2 x, secant squared, 1/2 x. And that was the original problem. There's the original problem up there. There's my answer, so it absolutely checked. Now on the last video I said that we were going to, foreshadowing that the same problem is on the next page. So when we started this, I did say, well, gosh, there does look like there's 2 inside functions. Which one should I choose? Should I choose u equal the tangent? That's an inside function. Or should I choose u equal the secant? And I went with u equal the tangent because the derivative of tangent was secant squared, and that was sitting in the problem. I like to see derivatives sitting in the problem. And so that's why I chose u to be tangent, because its derivative was absolutely sitting in the problem with no muss, no fuss. The derivative of tangent is secant squared. It was sitting in the problem. So that's why I chose tangent. But every once in a while, maybe you will choose the wrong thing. So let's do it again. But this time, I'm going to choose u equal secant, 1/2 x. So I'm going to rewrite my problem again. So I'm going to let u equal secant of 1/2 x. That's going to make du, derivative of secant, is secant tangent. Let's try to write smaller and neater so you can actually see it. Actually, what I'm going to do is I'm going to write it down below a little bit so it's not all crammed on there so much. Love the whiteout. By the way, I buy my own whiteout. This is not coming out of your tuition dollars. The reason why I mention that is I once had a student complain on teacher evaluations about my whiteout use. I buy my own. So I'm going to let u equal secant this time. That's going to make du, derivative of secant, is secant tangent, chain rule, times the 1/2. And then I'm going to go ahead and solve for dx. And so dx is going to be 2 du over secant. Actually, I'm not even going to bother solving for dx. I would, but I want to say something first. Right here, we need this this is not obviously in the problem. Now I wrote obviously because you could create it. You could create it, but it won't be as, you could create it. So we'll have to create it somehow. And that's not great. Now, sometimes you can create it, and we could here. So I could do this. I could say that this is 6 times tangent to the 4th x over 2 to the 4th, secant x over 2, secant x over 2, tangent x over 2. So there I created it. So I created it. Right? Need to create it. I created it, but I just made the problem harder. Made problem harder. And that is not the point to a U substitution. The U substitution is supposed to make it easier. So yes, I could create my du. Du, the variable stuff, has to be in the problem. If you have any choice, any hope of the problem working, that du has to be in the problem. So I was able to rewrite this. Instead of an x, since I wanted a secant tangent, I was able to rewrite this, breaking off a tangent, breaking off a secant. So it's still the same thing. Instead of tangent to the 5th, I have tangent to the 4th and tangent. Instead of secant squared, I have secant and secant. So it's the same thing, and I have created the du. So it's possible to make this work, and you could make this work. You could, but you made it harder. And if you find yourself making the problem harder, that's opposite of what we want a U substitution to do. So this wasn't the best choice, as opposed to what we did here, which very easily turned the whole thing in U to the 5th. That the derivative was obviously sitting in the problem. That when I picked tangent, the derivative was secant squared, and secant squared was sitting there. I didn't have to create anything. Here, if I pick secant, the derivative was secant tangent, and I could create it, but it made the problem harder, and so that's not really the best choice. Now, this one would have worked. But suppose it was a different problem, and you couldn't create this. You made your choice for U, you calculated du, and there was just no way to create it. It just wasn't there. That is usually an indication to not proceed at all. Now, there will be times where you could do something funky and still make it work, but that's not what we're doing in Calculus 1. In Calculus 1, if you calculate du and there is just absolutely no way to really get it out of your problem, that it's not sitting in your problem, at least the variable stuff, coefficients will take care of themselves. But if the variable stuff isn't sitting in the problem, it's not going to work easily, and it might not work at all. So try something else. Now, in this particular problem, we were able to create it, and I could make it work, but that wouldn't be the way I really wanted to go on this problem. So we will stop on this one because we already did it. We did it in a much easier way. Okay, next problem. They look very similar, but they are actually completely different. So I'm going to let U equal the inside function. So U is going to be 4x plus 5. Calculate du. And remember, du is du derivative dx. And so du is going to be 4x plus 5, which makes 4x plus 5 dx. There we go. Yeah, that's wrong, isn't it? I didn't take the derivative. Let's try to actually take the derivative here. 4 dx. And then solve for dx. And so dx equals du over 4. Okay. Now remember that dx on the top, you can just bring it over to the side. Then make my substitution, that's u. dx is du over 4. So step 4, that 1/4 can come all the way out in front. Then I've got 1 over 4, 1 over u to the 4th du, which I will remember is u to the negative 4 du. Step 5, still not necessary. I don't have room to write that, so I'll just tell you step 5, still not necessary. Then increase the exponent by 1, multiply by the reciprocal of the new exponent. And so that's going to be negative 1 over 12. Then I would drop that u down and replace it all at once because I'm running out of room. 4x plus 5 quantity cubed. So I dropped the u down so the negative exponent became positive. And then remember, u was equal to 4x plus 5. And there we integrated it. And the important thing I wanted to stay here is remembering that the way I did 1 over u to the 4th was to say that that's u to the negative 4 and then use my exponent rule. Very similar here as far as at least starting. I'm going to let u equal 4x plus 5. du is still going to be 4 dx. And dx is still going to be du over 4, starting it the exact same way. Four x plus 5 is still going to be u. dx is still du over 4. So I get 1/4, 1 over u du. And that's one of my absolute known forms. That integrates the natural log of the absolute value of u, and I will throw in the absolute value. I will be better than what my notes said. And then 1/4 the natural log of 4x plus 5 plus c. And so the real point here is the difference. They both started out the same way. But you've got to remember that when I have 1 over u to any other exponent other than 1, I use a negative exponent and integrate it. But when I can achieve the form 1 over u du, that's the natural log. And that was one of our choices back here when I gave all the list of the choices. U equals something to create the form 1 over u du. That's one of our known forms. And so very frequently, you will see substitutions that will create 1 over u du. And anytime you create 1 over u du, it's going to integrate to a natural log. And only the form 1 over u du. 1 over u to the 4th did not integrate to a natural log. Now, it doesn't necessarily have to be a 1 in the numerator. It has to be a constant. But a constant over u du integrates to the natural log. No other form integrates to the natural log. And in general, 1 over mx plus b integrates to 1 over m natural log of mx plus b plus c. Or in other words, 1 over linear integrates to the natural log. 1 over linear. Integrating other stuff to natural logs, 1 over u squared to a natural log, 1 over cosine to a natural log, 1 over the square root of x to a natural log, just wrong. You will lose lots and lots of points. End of this video.